That should do it. Okay, so we're taking a look at that compressor where we have air entering instead of steam this time. We have air that's entering, and then we have compressed air leaving. Now, this is where I want y'all to assume a pressure at state 12. It can be anything, as long as it's higher than the pressure at 11. I don't remember exactly what I said. I think I said assume something, a pressure ratio of something between 7 and 13. If I'm not mistaken, I could be wrong about that. But yeah. Don't look at that. That's wrong. Um, yeah, you're probably right about that. I mean, let's make positive. 12 and yeah, okay. Thank you. All right. Cool. All right. All right. So we have air coming from the atmosphere. So it's at so we know what P12 is. P12 is just the 1 ATM. And we can find P13 by assuming it. So we would need, okay, for today's class, I'm just going to say that it's 9. Assume whatever you want. I'm just going to go with 9, all right, for today's, or 10 to make it easy for my math. So we're going to say that P12 equals 101.325 and that P13 is equal to 1,000 there, okay? And this is in kPa. Okay, that's just to make it easy for me today. Assume whatever you want. You'll figure out what actually, the higher the pressure ratio you have, the typically the better, the more work that is required, by the compressor. So having a lower pressure ratio is a good thing, but then you also can't expand it as much in the turbine that comes afterward, after you heat it up. So it's kind of a balance. You have to find a good spot to put your pressure ratio at so that you don't have too much work being drawn by your compressor, but also are able to get enough work off of it after you heat it up. So y'all figure out what works best for y'all, depending on. There's I think it'll look like a bell curve or something like that. I think. I could be wrong. It depends on the pressures, but assume something, and I'm fine with it. All right. So again, mass balance, cool, M12 equals M13. Wow. Again. All right. Energy balance. So this one requires work of the compressor. All right. So N plus gen. Always going to write this out. Just like always. All right. Okay, so this is compressed air. So what we're going to be looking at is the CP, the changing of CP values, because that's what this is. That's what H13 minus H12 is. Okay, so we're gonna have that same integral this time, where we go from T, T12 to T13 of the moles at 13 in and this only works because we're assuming that it's an ideal gas. Honestly, I would say that this is the mole fraction. I'm gonna start writing that instead, because that just makes more sense to write as a mole fraction, because we don't know how much air there actually is. It's going to be dependent upon the amount of fuel that we have coming in to the combustion chamber down here in the Brayton cycle, where we have fuel at number 14. So it's the amount of air that gets put into the compressor is dependent upon the amount of fuel that is required for 300 megawatts of power, yet again. And so you can add up. The idea of this project is that all of the works that you have that come out of like a turbine, that come out of your turbines and go into your compressors, you can let's say I have two turbines in this project. So I have we can say that and a compressor. Let's just say that this requires work. So I could say that, some of the work that I get out of my turbine I could use in my compressor. Or I could do this. I could do like a double loop where I have some sort of work net that comes out of each, and I wouldn't make your math dependent on it, okay? But when I say dependent, I just mean that you should not make it such that you're forcing the work to be a certain thing based off of what the compressor requires. No, you shouldn't do that, because it's based off of the amount of fuel that comes through. It's just, if I have work coming out of a turbine, I could use it somewhere else. I could use it to like somewhere else in my system, not just send it off to the electric grid or whatever I'm trying to power. I could use it to help run my system. But yeah, I just wanted to mention that. But I'm gonna assume that it's a mole fraction. I mean, I'm just gonna start writing y instead, since a gas is a gaseous mole fraction, and it just makes more sense to write it like that, because then it's dependent upon. You're still saying that it's a work bar, like right here, instead of a per pound of mole, or sorry, since it's not per pound. Sorry, since it's a mass, not a mole fraction. It would make more sense as a mole fraction. All right, and then you write this integral out. You just keep going, and you solve it, basically. You use your y13 for, I'm just not going to write y13. I'm just going to write y for, O2, and then your big, long CP. The problem here is that you don't know what T13 is. So how are we going to solve it if we don't have y13? We have to do an entropy balance, because we have two unknowns. And this is all for, I'm just going to say that it's all O2 on the outside. And, sorry, I didn't write the sum right there. It would definitely be that. and it's all multiplied by some r value. All right, just like what we were doing before. Just like what we were doing before whenever we found the outlet temperature, or outlet temperature for state 3. Except now this is what work is equal to, instead of it being equal to 0. And so now it requires also an entropy balance. And I might be wrong, but I'm pretty sure that the only way that you can solve it is by assuming that delta S, is assuming that it's reversible. I believe that is, yeah, honestly, I think that's the only way that you can go about solving this, unless you do something more complex that I'm not even aware of. So we write it up. And I know I said irreversible at the beginning of the project, and then I realized that you can't do that for the Brayton cycle. So we're saying for both the compressor and the turbine in the Brayton cycle, we're going to assume it's reversible. All right. Why am I doing that? All right. And for ideal gases, and for when it's reversible, we can say, I mean, there's still a mass of, like, since there is an inlet, we can still say this. And this just basically, I'm gonna make this 0. So 0 right here. Actually, I think this is, I don't like this. I don't like what I'm doing. And that's what you can do for a entropy balance for an ideal gas, including air. Except this time our CP, again, is changing. So we have to plug in that whole value. And you basically, but this term, the R over P term, doesn't have to change. The only thing that really needs to change, that's dependent upon per component, is the T, is the CP, because the CP values change. So our integral from T12 to T13 is equal to Y02, you know, that whole thing again. You write out this again, okay, except I divide it by T. So and that's how you would work the entropy balance over T. Okay? And you do the same thing for nitrogen. Okay, and then you just tack on the end of that, which is this part, or not equals, minus R over P. All right. So are there any questions about that? I don't know if there would be. There might be. Who knows? Because if you did assume that there was delta estrogen, you'd have 3 unknowns and 2 equations. And that wouldn't be a good thing. Yo. Of an ideal compressor, yeah. A reversible compressor, I mean, yes. Ah, there we are. Thank you. Yeah, you would do that. That's how you solve it. Okay, yeah. So that would be, yeah, thank you. I don't know what I was thinking. Okay, so yeah. You would take the this would solve for the work of the compressor that's ideal. Yeah, yes. Okay. So I could say to start that we're assuming that so I'm just gonna change around a little bit about what I said. This is definitely correct. Now that you said that, Jake, thank you. Now I definitely don't have a worry about this being incorrect, other than the fact that I'm gonna call this step 1, assume reversible. All right, so step 1, assume it's reversible. Okay, so this is the work of the ideal pump. Okay, once you solve for the work of the ideal pump after you get T13, so you rearrange the entropy balance. So you solve this for T13. Okay, and that's technically the ideal temperature for an ideal pump. Okay, and then in the entropy balance. All right, and then you solve for the work of the compressor, ideal, and the energy balance. All right, and then you take the ideal work of the compressor, multiply it by its isentropic efficiency, and get the work of the compressor that's real. All right. Now I have the work of the compressor that's real. Now I can solve for T13 using my energy balance, the real one, in my energy balance by back flushing, I guess, if I'm going to call it that. Sure. Okay. So this is basically step 2 right here. Step 2, and it's now irreversible. Okay? Apologies for that confusion about assuming reversible at the beginning. Now, once you get to that boiler, you'd assume that Give me a second. All right. After the compressor, we have another combustion chamber. I guess you could write it like that, you know, since we're saying that's the combustion chamber. So this is the air and this is the fuel, okay? Except this time the only difference between the two is that the air is now compressed and the fuel enters at the same pressure as the compressed air. Okay, so P13 equals P14. And that doesn't really change a lot when we've already stated the fact that there's 100% conversion. Now, in your reactors course next semester, that would matter. Your pressure drop could matter. I mean, actually, I don't even know if y'all get the pressure drop in that class. I don't remember. But your pressure drop across a reactor can matter, but this is a combustion chamber where it kind of doesn't matter because all of it's about to get reacted. It's kind of a crude reactor, and so we call it a combustion chamber because it's like, it's like burning wood. Pretty much, eventually, at some point, it's all going to get burned. And what you're going to use, and so pressure drop doesn't really matter, and I'm just making sure that's aware. And the higher the pressure usually means the higher the conversion, especially in the gas phase. But here it doesn't matter since we've already stated that it's 100% conversion. I just want to make y'all aware of that. That's all. What are we saying? Again, across the combustion chamber, we're saying that the Q, this is adiabatic, okay? We're going to assume that it's adiabatic. And it's basically, you've already done this. You've literally already done the math for this, or at least I think most of y'all have. It's the same math as the other combustion chamber, literally the exact same, except now you might have a different temperature outlet at 15 than what you originally got. And the higher the temperature at 15, pretty much the better, because combustion chambers can handle a lot of heat. I mean, I don't want to see something in the millions in Celsius. That would, we don't have a fusion reactor. But other than that, it's pretty much the higher the better. You know, something like, I wouldn't expect to see anything above 4,000 Celsius, but I really hope I don't see something above 4,000 Celsius. I'm expecting something like 2,000, 2,500. Honestly, if you get to 1,500, that's fine. Like no worries. If it's 1,000, I don't care. You know, I don't want to see, like, the upper limits would be like 2,500. Okay, it just depends on what you assume your pressure ratio to be. It's the same integral, you know, where you have two different. What am I saying? Where you have two different entering gases, where you're going to have, you know, the integral from T13 to some T ref, okay? And then that's going to be plus times the y of the air at 13 times the Cp of the air dt, okay? And this is going to be plus T14 T ref of the y of the fuel at summation sub I and sub I, sorry, I just forget those. Summation Cp of fuel sub I dt. Okay, and this is equal to delta H in. Okay, and then you do the, the same things for the reaction plus delta H out, and this all equals 0. And then you find, you use this to find T15. All right, and then you do the exact same thing that you did for the compressor, just backwards. When I say backwards, I just mean that it's expanding. So it's basically, it looks exactly the same. It's just for the two different temperatures. And yeah. Yep. Oh, definitely. Definitely assume that it's 298. Those, pretty much your reference temperature is always going to be 298, no matter like what you're doing. Because the way that tables work is that they often have the delta H's of reaction. The delta H's of formation. Okay, so yeah, let me get into that just a little bit again. So pretty much all of your reference temperatures, Tref typically equals 298 K. Okay, and that's because your delta H of formation is at 298. Okay, and that doesn't just go for the reaction terms. Okay, so this is a latent form of heat. This is a reaction. You use this enthalpy whenever you're dealing with reactions. You also have heat of vaporization. You have heat of fusion. And these are sensible, and this is whenever you change phase. Or no, they're all latent. No, they're all latent heat. But this is whenever you change phase. This is for whenever you change from a liquid to a gas. And this is whenever you change from a gas to a liquid. So this is liquid to gas. And this is gas to liquid. And all of these are also, I believe, at 298 K. They're all at that reference temperature. So pretty much every time that you deal with this, I think that I don't know if you've already started. I know Dr. Griffith mentioned a valve the other day, and I think that it might, like a flash valve. Did he mention that in class? Okay, I wasn't sure. Well, whenever he does start to go into detail, you're going to start doing equations with delta H of formation, delta H of fusion. Did I say formation? I meant vaporization. But you're going to deal with these two, all right, with that valve, and you're going to find out what parts of it become a liquid or remain a liquid, and what parts of it become a gas. And you'll have to bring something to a reference temperature of 298 yet again. And it pretty much works like that across the board. You'll bring something down to a reference temperature or up to a reference temperature, depending on what temperature it was, and then you'll bring it up, or you'll bring it down to whatever temperature it was at. For valves, I believe that the temperature is actually going to go down. I believe, could be wrong, depending on what you got. It should typically go down. For the combustion chamber, it went up. But so that's why I like to draw it like this, because it could change whatever direction you want. And that's that table where we had, temperature, and I don't even know. I think this is a mono axis. It's just kind of there. Delta H in, delta H of reaction. Honestly, reaction, I don't want to say that. I just want to say latent. Delta H of latent, the sum of the delta H's of your latent. Okay? And for that combustion chamber, the sum of the latent heats was equal to the delta H of the reaction, because we didn't have to deal with phase change. And yep. I like that. Okay, are there any questions about what I've done so far? I'm done lecturing for today. about this. I'm just here to answer your questions now. Thank you. No questions? Nobody's got anything? All right, cool. That's good. That's good. How's everybody doing? I wasn't in a class yesterday. What did Dr. Griffith go over? Cool. Okay. Okay. All right. All right. Guess we could, fuck it. We got, what, 10 minutes? This is my old project. Don't pay attention to this one. This one's like my reference page. It's not useful at all. If it would open, that'd be cool. Huh. Well, that's fine. We're gonna. Do we have the temperatures? Oh, okay, so yeah, I guess I could tell y'all like what some good temperatures are for state 3 and state 4. So this is the temperature I got in Kelvin, and the temperature I got in for 3 and 4, for 3 and 4. What is everybody getting? What temperature have y'all gotten for temperature 3 and temperature 4, or it's specifically temperature 3 right now? Okay, cool. What else? Just trying to get a rough ballpark of what everybody's getting. 2190. All right, cool. That's mine right there. 2193 as well. Awesome. I think the first time I did this, I got 2195. All right, all right. Yeah, and depending on what you assume in your Rankine cycle, your temperature is going to be all over the place for that. What temperatures did y'all assume at state 6? What were y'all getting there? Coming into the turbine. $1,317. All right, cool. Interesting. Wait, you did yours in Fahrenheit? Oh man. All right. That will be fun. Yeah. Yeah. I did want to show y'all this. Because I worked a good 3 weeks on this and it still doesn't work right, but If you look here at the thermodynamic tables, like I have this thing that I made, and I've been working on it. It's still in beta. I I I'm trying to program it a steam table calculator such that it would give you, yeah. Why is it never showing up? All right. But such that it would just give you the rest of the states depending on what you have. So if I know that the entire saturated region works correctly and flawlessly, but the superheated region has given me a lot of trouble. But it's just kind of, I don't know why my stuff isn't opening, and I'll have to figure that out later. But well, whatever. I did find a better calculator though that's online. So I'm gonna go ahead and post that one to Moodle. It looks like this. And open in the new window. Oh, I'm at tab. Okay, so I'm gonna post this website to Moodle. It's literally all of your steam table calculations that you would need to do, all your interpolations. Yeah, you don't have to do those anymore. They look like this. I mean, okay, probably on the test you'd have to do them, but like, you know, you don't have to. You plug in whatever you want. You can have the temperature, or let's take a look at saturate or the superheated region. All right, so we're going to take a look at the superheated region, and so I have, for instance, a pressure and a superheated temperature. So I'm going to type in make sure they're absolute, otherwise they wouldn't work right for regarding this project at least. So I'm going to say that my pressure is what, 2, no, no, megapascals. So 2,000, and I know that 1,000 is on the list somewhere. I can calculate that. It'll give it to me. It'll give me all of these values. What is this? Too high? Okay, so I'll bring it down. Let's go with 200. Let's hope that works. Oh, well, come on. You know, you have to be in the superheated region, otherwise it won't work right. There we go. So now that I'm in the superheated region, this works, and it'll give me all of the values that I would ever need. So the entropy or then that's in joules. This isn't joules per kilogram. I can change it to whatever, but it'll give me the entropy. It'll give me the enthalpy. For some reason, it'll give me the speed of sound, and I don't exactly understand how that works, but I'm just kind of messing around right now. This isn't really like necessary as far as like what we're doing as far as coursework goes. I'm just showing you this because I thought you would appreciate it. That is all. So I'll post that to Moodle if you want to see it. It'd be helpful. It's free. That's the cool part. I mean, I didn't have to sign up or anything. I just logged in. I just like typed in this website and it's there. So yeah, a lot of these you actually have to pay for, and I'm happy I found this one.